So now that we've done some work with Ampere's law, we can see that you need some symmetry for easily evaluating those integrals. That can be limiting. So we can introduce a different method called the Biot-Savart Law that's letting us evaluate the magnetic field for a current flowing on any path. So the Biot-Savart Law really says that a current flowing on any path can be considered as many tiny current elements. So if we have many tiny current elements, each of those tiny current elements should have a tiny contribution to the magnetic field. And it should look like this. So we've got mu 0 times I over 4 pi. And then we're going to have that tiny element, so that little bit of length of this current element, crossed with an r hat over r squared. And here again, r is this radial distance. So that just means straight line distance, a ray. A radial distance to a point where you're evaluating or measuring the magnetic field. Right? So if r is that radial distance, r hat is the unit vector in that distance. So it's just got a length of 1 pointed in that same direction. And r squared is that distance. So the cross product is where the right-hand rule comes in. And we can evaluate that further with the cross product as dl times sine of theta. So if r just has a length of 1, that's implied in here, and sine theta, or theta, is the angle between our vector dl, so our little length of current element, and our vector r. Now here in your book image, they use, again, ds instead of dl that I'm using in my notation. So if we want to find the total magnetic field at a certain point, we need to add up all these little bits of contribution. So finding the magnetic field by adding up all these little bits of contribution, you guys have all taken calculus. Adding up the little bits of contribution is just saying take that integral, right? So we're going to take that integral along the path. So the Biot-Savart law looks like our total magnetic field that we're evaluating at some point is going to be from the current through each of these current elements evaluated with that cross product and the square of the distance. So it's kind of like Coulomb's law where we're doing a vector sum. You see there's a cross product here, so the direction matters. We need to add x's to x's and y's to y's. In this example that's in the image to the right-hand side of the screen, you can again do the right-hand rule for your cross product. We point our fingers in the direction of the first thing. So they have it labeled DS. We would point our fingers in that direction. We would rotate our wrist around so that our fingers would naturally bend in the direction of the second thing, that R hat. So we would rotate our wrist around so our fingers naturally bend in that R hat direction. And we would get that, at least at this point, the magnetic field would point out of the page due to that little bit of current element. Now over here, if we do the same thing and we look at this R hat direction, we get that it would point into the page, right? So move your right hand around, double check that you understand how that's working. So for the Biot-Savart law, the little bits of magnetic field are due only and entirely to the current element that we're considering. And the current element that we're considering here that is creating this dB is that current through a little length we call dl or ds in your book. To find the total magnetic field, you've got to include all currents that are contributing to this space, right? So if we're only looking at this wire, we're only looking at the magnetic field caused by this wire. To get the magnetic field overall, we'd have to include any circuit elements, any current elements nearby. So we can do an example with this Biot-Savart law. We can look at the magnetic field due to a long straight wire. So I wrote here now with Biot-Savart because we have already done this at the beginning of the chapter, right? Remember, experimentally, it was already determined that the magnitude ought to be mu 0 over 2 pi and I over r. All right, so we already know what we're headed towards. Can we get it to happen? So Biot-Savart says that we're going to find the magnetic field due to this wire by adding up all these magnetic fields, right? Biot-Savart says that adding up all those magnetic fields should look like something like mu 0 times I. We have no, I is the same in all these little DS's of this current element over 4 pi. And we're going to do ds, I'll switch to their notation, crossed with r hat over r squared. So we're going to pick an arbitrary point P that you can see in this image up here. And we're going to define everything relating to how close we are to P and all that other stuff. All right, so generically, here's Biot-Savart. How do I attack this though? Well, first, I am going to evaluate just this cross product, right? I'm going to try to get that cross product of ds crossed with r hat in a form that makes sense. So the way I have defined my current element, I have put my P on a y-axis and I've said my current is going along the x-axis. The reason I've done that is to try to make my life easier so that when I do a cross product, I know that ds crossed with r, those two vectors are in the xy plane. And so ds crossed with r is going to give me something of a certain magnitude whose direction is going to be in the z direction or the k hat direction. Now, I want to define that cross product, right? So a cross product is the magnitude of one thing times the magnitude of the other thing times the sine of the angle between them. Because I put ds in this x direction, I can just rename it dx, right? So that's the magnitude of the first thing. The magnitude of r hat, because it's a unit vector has a magnitude of 1. So there's an implied times 1 here. And then I'm just going to switch this to parentheses. And then times the angle in between them. So let's look at what the angle between these two things are. So between the positive x-axis, actually, let's look at it this way. Between this ds and r is this angle right here. So if this is a right triangle and that thing up there is theta, the angle between my y-axis and this r, this angle is just 90 degrees minus theta. Yes? All right, make sure that makes sense to you. And so, and I'm actually going to write that in terms of radians. So we'll do pi over 2 instead of 90 degrees minus theta. And of course, this is in the k hat direction. Okay, so once I've evaluated that, I want to substitute this into the equation. So my second step is I'm going to put this into my Biot-Savart equation. When I do that, I'm going to have something that looks like dB equals the magnitude dB in the k-hat direction at that point, right? Equals mu 0 I, so my permeability of free space, my current, 4 pi. And we're going to put this in where the cross product was. dx cosine theta over r squared k-hat direction. All right, so you might be going, wait, cosine theta, you've got sine of pi over 2 minus theta. That just happens to be a trig identity that I could take this sine of pi over 2 minus theta and say that is the same as cosine theta. So that might not be something you have in your back pocket, but it is a trig identity that is going to make our lives a little bit simpler. All right, so we want to clean this up to one variable, right? We need to do an integral. We only want to be integrating over one variable. So we're going to use geometry here to do that. We're going to say that R is the hypotenuse of this triangle here. So R is related to A, which just happens to be a constant location of the point where we're trying to measure our magnetic field. So R equals A over cosine theta. And no matter where we move, right, if we move and look at the contribution of this little current element, that A remains the same. And cosine theta is the thing that's changing. All right, what else can we say? We can say that X is related to minus A tangent theta. All right, so we can get everything in terms of our theta. Okay, so now the dx that we have in our equation, we just take a derivative of x with respect to theta. So the derivative of a tangent is going to give us a function called a secant. And we're going to have secant squared theta d theta as our dx. A secant squared we could write in terms of a more familiar function, 1 over cosine of theta. Okay, so now we have everything in terms of theta. That's going to be the variable we integrate over. So I can write my Biot-Savart equation in terms of those different things. So I still have these constants out front where I had dx, I am going to substitute in a d theta and cosine squared theta. The negative sign got out here in front of all my constants. Where I had 1 over r squared, I'm going to substitute in this for 1 over r squared. So cosine squared theta over a squared. And don't forget, I also had a cosine theta left over, right? So just double check that with the previous slide that I had. This is my dx. This is my 1 over r squared. And my cosine theta was already there. Okay, so I have all that stuff. I want to clean it up a little bit further and say that dB should then be equal to my negative sign, don't forget that, mu 0 I over 4 pi a cosine theta d theta. Okay, this is already starting to look a little cleaner and a little better, trust me. So finally, once we have this all cleaned up and in terms of one variable, what we're going to do is integrate to get our total field at point P that is being caused by all these little current elements. So we have to do this. what we're going to be doing, since we're integrating with respect to theta, is we're going to put in our equation for dB that we came up with for this specific case, right? So each of these are for a specific case. And we are going to go from being all the way out here where we can say our relationship is theta 1 away from our point P, to all the way over here where we can say our relationship is theta 2. So we're integrating from theta 1 to theta 2. And most of our dB comes outside of the integral because most of it is just constants. So we just have to integrate cosine theta d theta. That's a pretty easy thing to integrate. We're going to get rid of our negative sign because of the integral of cosine theta being negative sign. And we are basically, we're going to get rid of our negative sign by switching the order of how we're subtracting things, right? So we come up with this solution. And this is just kind of a generic solution of what does the magnetic field due to a long wire look like. So if our wire only is a short segment, we can still figure out what the magnetic field looks like at a certain point by knowing what angle we get by looking at either end of that wire from this point. But if we have a very long wire, you can picture that theta 1 is going to head towards pi over 2, right? It's going to head towards 90 degrees. And that theta 2, if we're measuring in the other direction, is going to head towards a negative pi over 2. And so if you substitute that in to our sine theta 1 minus sine theta 2, you're going to get a 1 and a negative 1, and so that will head towards just the value 2. So for a very long wire, this simplifies. This simplifies pretty much to what we expect, which would be mu 0 over 2 pi, because that 2 and that 4 cancel slightly. And then I over A. And A is, again, that radial distance away from our wire. So with the Biot-Savart law, we can show that we get the thing that was expected from our experimental results at the beginning of the chapter. All right, I'm going to pause here and pick up with another example in the next recording.